What we're looking at today is different types of measures of variation. We've already looked at central tendencies, measures of central tendency like the mean, the median, the mode. Today what we're going to look at is types of variation, and that's looking at how far items are from the actual mean. The first type of variation that we're going to look at is the range. The range is just the highest value minus the lowest value, and we always use the symbol R, and this is affected by extremely high or low values, meaning that your range drastically changes if you have extremely high or low values. So let's look at an example, and our example is regarding airport parking, and I have here the number of short-term parking spaces at 15 different airports shown, and I want to know what the range of the data is. So the first thing that I want to do is I want to find out what is my highest value. So you want to know the highest value, and you want to know what the lowest value is of your data set. Well, looking through your data, 9,822 is your highest value, and it looks like 203 is your lowest value. So our range, again, is our highest value minus our lowest value. So 9,822 minus 203. So the range is going to be 9,619. So we have the range of the number of short-term parking spaces is 9,619. So just remember that the range, again, your range is the highest minus your lowest value. And remember to actually do that subtraction. Okay? This is one type of variation. Now, data variation is the difference or the distance also that each data point is from the mean, and this difference is also called the deviation. But we also want to look at a second type, which is called the population variance. This is the average of squares of the distance from each value is from the mean. So in other words, this distance from the value, which is the deviation. So this distance right here is also known as the deviation. How far a value is from the mean, that's known as the deviation. And for population variance, we use this symbol, sigma squared, and this is specifically for population variance. Okay, the formula for population variance is going to be sigma squared is equal to the sum of these deviations, our values minus the means squared, divided by n. Now let's go through here and look at what each value means here. So x is just our individual values. Our individual values. Mu, remember from previous lessons, is our population mean. and our capital N is the population size. How many values are in our population? Like in the previous example, we had 17 different parking lots that we were looking at. So our N would have been 17. It's not the sum of them, it's just how many are there. Okay? This is how we find the population variance. Now, we don't usually do a whole lot with the population variance. We use the population variance to find other things. We don't really talk about the population variance a whole lot. It does help us though. Now remember, there's a difference between population and sample. Population is where we have the entire population. Sample is where we just have a small sampling of things. So you do have to know the difference, because the sample variance will actually have a different formula. And we will look at that a little bit in just a little bit. Now, once we find the population variance, then we can go into finding the population standard deviation. And this is really the distance, what the standard value is for each of the data points from the mean. What is that standard distance? What is the average distance really from the mean if we standardize it? And it's really just the square root of the variance. So if on the previous we used sigma squared, notice here we use sigma squared for population standard deviation, or I'm sorry, population variance. For standard deviation, since it's the square root of the variance, we're just going to use sigma. And the formula is sigma, which is the square root of sigma squared, or it's the sum of our x minus mean values squared divided by n, and I'm going to take the square root of that. So I literally take the square root of my variance. Now, just like where we had rounding rules for mean, median, and mode, we're going to have rounding rules for variance and standard deviation, and they're going to be the exact same as our mean. Your final answer should be one more decimal place than your original data. So if your data has no decimal places, then your variance and standard deviation should have one decimal place. If your data has one decimal place, then your variance and standard deviation should have two decimal places. It needs to be one more place than your original data. So let's look at how we would actually find the variance and standard deviation. Okay? These are the 6 steps that we take for finding population, variance, and standard deviation. And they're actually going to be the same for finding the sample variance and standard deviation, just using a little bit different formulas. So I would make sure that we know these 6 steps. But let's look at this. The first step is to find the mean of the data. And remember that for population, the mean is we add up our data points and then we divide by how many we have. So we sum up how many our data values and then we divide by how many we have. The next step is we find the deviation for each of our data values. Remember that the deviation is we take our value and subtract the mean from it. Then we're going to square each of those deviations. So we're going to take that and square it. And we're going to do this for each of the values, each of the data points. Once we do this for each of the data points, we're going to add up this value for each of the data points. So we're going to sum up our x minus mu squareds. So add them all up. Once we add them all up, we're going to divide by n. And that will give us our variance. So step 5 gives us our variance. So that actually gives us our variance. Step 6 will give us our standard deviation, and remember that that is just taking the square root of what we just found. So taking the square root of everything that we just found. Okay? Now, these 6 steps seem a little bit daunting. It is actually much easier if you kind of follow this table right here. If you set it up into these 3 columns. The first column is putting all your values in this first column. So if we have a data set that has the numbers 1, 2, 3, and we can do this, we will put the numbers 1, 2, and 3 here. So our first step was to find our mean. So our mean, let me redo that. That looks a little bit sloppy. So our mean is going to be 1 plus 2 plus 3, and I have a total of 3 numbers, so I'm going to divide by 3. So that's going to be 6 divided by 3, which is 2. So my mean is 2. Okay? So that was my first step. My second step was to take each data point and subtract the mean from it. So I'm going to take 1 minus 2, which gives me a negative 1. 2 minus 2, which is 0. 3 minus 2, which is 1. So that was step 2. Step 3 is to square each of those values. So I'm going to take negative 1 and square it. It's very important that in column C, all your values are going to end up being positive. Negative 1 squared, which is negative 1 times negative 1, becomes positive 1. 0 squared is 0. 1 squared is 1. Step 4 is to sum up this column right here. So I'm going to add this up. So I'm going to get, this is going to be my sum. So 1 plus 0 is 1, plus 1 is going to be 2. So that is my sum there. Okay? So the sum of my x minus means squared is going to be 2. That was step 4. Step 5 is to divide by my capital N. Remember that capital N is basically how many rows I have. I have 3 rows. So capital N is 3. So my variance is going to be the sum of my x minus my mean squared. And this is getting really sloppy, sorry. Let me erase that whole thing and try again. Okay, the sum of my deviations squared divided by my n, which is going to be 2 divided by 3. So I get, and remember I want to, since my values are in whole numbers, if I put this in the calculator, this is what I get, but rounding rules, my data points are in whole numbers, so I want to round this to one place more than my data. So this is going to be rounded to 0.7. So my variance is 0.7. Then to get my standard deviation, I'm just going to take the square root of that. So the square root of 0.7 is going to be 0.8. And this was just a very quick example of showing you how to use this table. We're going to go into a much longer example of this, but you can see how using the steps up here, it looks kind of, oh, how do I do this? But if you organize it in this ABC column type, it will help you much more. Okay, so let's look at an actual example of this. And the example that we have here is find the variance and standard deviation for the number of months a brand of paint lasted before it faded. And it tells us that this is the population. So we're going to be using the same thing that we have before. So we're given that one brand lasted 10 months, one brand lasted 60, one lasted 50, one lasted 30, one lasted 40, and one lasted 20. So I've already made the table, columns A, B, and C. Here's my X column. I've just put my data points in here. My B column, which is for my deviations, and then for my squares that I'm going to do. Recall from the steps, step 1 is to find the mean of the data. So the mean is going to be to add these up, and then we divide by how many we have. We have 1, 2, 3, 4, 5, 6. So I have n is going to be 6. So I have 10 plus 60 plus 50 plus 30 plus 40 plus 20. That is going to be 210 divided by 6. So my mean is 35. So then in column B, I'm going to take 10 minus 35, which is going to give me a negative 25. And I'm going to do that all the way down. So I'm going to get a positive 25, -15, negative 5, positive 5, and a negative 15. Okay, and all I did was take 60 minus my 35, 50 minus 35, 30 minus 35, and so forth. Now I'm going to take these numbers and square them. So I'm going to take negative 25 squared, and remember that all your final numbers in column C need to be positive. So that's going to be a positive 625. So this will be 625. 15 squared is 225. Negative 5 squared is a positive 25. This will be a positive 25. And this is a 225. So this is step 1. This is step 2. This is step 3. Step 4, remember, is to add all these numbers up. Okay? And so whenever I add all these numbers up, I'm going to add each of these numbers up, and let's see what I get. I get 1,750. So the step 4, which is the sum of my x minus means squared is 1,750. Step 5 is to take this number and divide it by n to get my variance. So step 5 is to take this and divide it by n. So I'm going to take my 1750 and divide it by how many numbers I had, which was 6. So my variance is going to be 291.6. Oh, that's messing up on me again. Let's try that again. 0.6667. What are my data points in? They are in whole numbers. Therefore, I have to round my variance to what? I have to round my variance to 1 decimal place. So my variance is going to be 291.7. So there's my variance. Step 6 was to find the standard deviation, which is just taking the square root of this. So I take the square root of this. So I'm going to do the square root of 291.7. Which is going to give me 17.079, which whenever I round that properly will give me 17.1 as my standard deviation. So the standard deviation for the number of months a brand of paint lasts before fading is approximately 17.1 months. Okay? Again, using this table will really help you out in the process. Now then, let's look at what we do for sample variance and standard deviation. As I said, it's the same type of concept, it's the same thing as the population, it's just used with a sample. Therefore, we're looking at a small version of the group. We're not looking at the whole group. For a sample, the symbol for the variance is s squared. Recall back when we were talking about the mean and everything, we looked at the mean of the population as being a Greek letter and the mean of a sample being an alphanumeric letter. It's the same thing here. The symbols for populations will be Greek letters and the symbols for samples will be alphanumeric. Also here, instead of dividing by n, we're going to divide by n minus 1. So the formula for sample variance is going to be s squared is equal to the sum of x minus, and I'm using x bar this time because that's the mean of a sample, squared divided by n minus 1. Same type of thing, except for again I'm dividing by n minus 1 this time, and it's just so it would be unbiased. I have a little bit of leeway there. Okay, looking at the sample standard deviation, if the sample variance, that should say sample standard deviation instead. out of variance. That should be deviation. I apologize. And I've got too many letters there. Let me try that again. Let's see here. There we go. Sample standard deviation. So if the sample variance uses the symbol s squared, the symbol for sample standard deviation is going to be s, and we're going to do the square root of s squared, which is going to be the same type of concept, and take the square root of it. Use the exact same steps to find the sample variance and standard deviation, except we divide by n-1 instead of n on this. Okay? So, let's look at an example. The increases in cents in cigarette taxes for 17 states in a 6-month period are as follows. Now we know this is a sample because it only gives us 17 states. We know that there's 50 states. We want to find the variance and the standard deviation for the data. So I've already drawn the table for us here that gives us this information, our column A, B, and C. Remember that column A is just your x values, column B is going to be x minus x bar, and column C is where we're going to square that column B. Okay? First thing that we have to do is we have to find our x bar. So I need to add up all of these and divide by how many there are. Well, I already know that there's going to be 17 because it tells me that. When I add all of these up, add each of these up, that is going to give me 652. So my sample mean is going to be, if I do this, I get 38.35, but my rounding rules say my data has 0 decimals, so I need to round everything to 1 decimal. So my x bar is 38.4. Now I'm also going to put over here that my n is 17 because remember that's what I used right here. How many data points I have. Okay? So here I'm going to take 60 minus 38.5, which will give me 21.6. And I'm going to do that all the way down. Okay? So I get negative 18.4, one point six, 1.6, 6.6, negative 26.4, negative 4.4, 12.6, negative 8.4, 31.6, 3.6, negative 7.4, 30.6, negative 6.4, negative 30.4, negative 20.4, and 11.6. And again, what I did was I took each one of these and subtracted 38.4 from it. Okay? Next step is to square each one of these. So I'm going to take 24.6 and I'm going to square it. and I get 466.56. In this column, I don't like to round very much, so I like to leave 2 to 3 decimal places here, if possible, just so that I have enough, and I'm making sure that I'm not cutting off too many decimal places. Okay? So I really prefer to make sure that I'm leaving more than what I have to have here. So let me go ahead and fill this table in. You can also do the calculations. Remember that this has to be all positives here. 2.56, 43.56, 696.96, 19.36, 158.76, 70.56, 998.56, 12.96, 54.76, 936.36, 40.96, 924.16, 416.16, and 134.56. Okay, then I'm going to add up this column. So the sum, of my x minus x bars squared is going to be 5,317.92. So my, not sigma squared, we're working with samples, so my s squared is going to be my 317.92 divided by 17 minus 1. So that's 5,317.92 divided by 16. So my s squared is going to be 332.4. Then I take the square root of that to get my, remember that this is my sample variance. I take the square root of that to get my standard deviation. So my standard deviation is going to be 18.2. Okay. Now then, this is for ungrouped data. We do the same type of procedure with grouped data. It's a little bit differently. We have much different formulas. Here I have the sample variance. We don't use population for grouped data because we never know if we have the entire group or the entire population. So we always use the sample for grouped data. Here I've already given you the formulas for this. Let me go over a few of the things. Remember that N is sample size. Your F is your frequency. X sub m is your midpoint. Okay? Midpoint of that category or of that class limit. So we're going to have to be finding the midpoints of these things. And it's much easier, again, if you follow this table right here. Put it into an A, B, C, D, E category. This will be the sum of your frequencies. This is the sum of your F times X sub m squared. This is the sum of your F times X sub m. Okay. And so putting it into these will actually help you out a little bit. Doesn't make a lot of sense until you see it in an example. So let's look at an example. The data represent the number rate per 100,000 individuals in a sample of select cities in the U.S. Find the variance and standard deviation for the data. Okay. So this table gives you the class limits and their frequencies. And I've already started the table to find the variance and standard deviation for us. What we need to do is we need to find the midpoint and go from there. So what we're going to do is remember that the midpoint is taking our class limit 5 plus 11 and dividing by 2. Okay, so 5 plus 11 divide by 2, and that gives us an 8 for our midpoint. And we're going to do that all the way down. So I take 12 plus 18, divide by 2, and I get 15. And again, I'm going to do that all the way down, and that will give us our midpoints here. Okay? Then for this column, I'm going to take frequency and multiply it by my midpoint. So I'm going to take 8 times 8, which will be 64. Then I'll take 5 times 15, and I get 75. And I'm going to do that all the way down. So I get 154, 29, 36, and 129. This last column is where I take the frequency times the midpoint squared. Or what I like to do is I like to take column D and multiply it by column C. Because I've already got the frequency times the midpoint, I just need to multiply it by the midpoint again. Okay? So it's basically 8 times 8 squared, which is going to give me 512. So if I square my 15, that's going to give me 225. Multiply that by 5, I get 1,125. Then 22 squared is 484. Multiply that by 7, that's going to be 3,388. 29 squared is 841. Multiplied by 1 is 841. And those should be 8s. So let me draw those as 8s. 36 squared is 1296. Times 1 is 1296. 43 squared is 1849 multiplied by 3 is 5,547. Okay, so now the question is, what do we do now? Our formula for variance, let me move that down a little bit, says this: n times the sum of f times midpoint squared minus the sum of f times midpoint, that quantity squared, divided by n times n minus 1. Okay, so I know that I need to add up my n's, which n is how many total I have here. So that's 25. I also need to add up this column, which is going to be let me check that again. $487, and I need to add up this column: 512, 1125, 3388, 841, 1296, and 5547 is equal to 12709. Okay. Here's where everything goes in this formula. My n is 25. This sum of f times xm squared is actually this last column, minus 87, that value squared, divided by 25 times 25 minus 1. So notice that it's column B times column E minus D squared, divided by B times B minus 1. And sometimes I'll put it on there that looks like this. That's column B times column E minus column D squared over column B, B minus 1. Kind of helps me whenever I'm looking at the different columns a little bit. Okay? May confuse you some, I'm not sure. If you need help on this, please let me know. But whenever I do this calculation, I have to remember to simplify the numerator first. So 25 times 12,709 is equal to 317,725. 487 squared is 237,169. This is 25 times 24. So 317,725 minus 237,169 is going to be 80,556. 25 times 24 is 600. and I get 134.26, which rounds to 134.3 is my variance, and that should be sample, so I need to change that to s squared. So my sample variance for this is 134.3. So my sample standard deviation for this is the square root of 134.3, which is going to round to 11.6 for this grouped data. Grouped data does go much more into detail like this. Okay? Variance and standard deviation are much more in-depth, a little bit more detailed. It is going to take a lot more practice. Now then, if you have things that have different units, such as you want to compare your grade in two different classes, one uses points, one uses percentages, or you want to compare your income to your age, different things like that, we can't compare those using variations or anything like that unless we use something called the coefficient of variation. This allows us to compare their standard deviations and know which one is more variable. Once we know which one is more variable, we can tell which one is actually better based on the mean. Okay? We denote this with CVAR, and it is the standard deviation divided by the mean. So for population, a population, the CVAR is going to be the standard deviation divided by the mean times 100. We always multiply it by 100 because that way it's in whole numbers. Change it into basically a percentage. Okay? For a sample, and for some reason my pen does not like me today. For a sample, it's still going to be denoted CVAR. It's just S divided by X bar multiplied by 100. So notice we calculated the exact same way, it's just the symbols that we use change. Okay? So let's look at an example. The average age of the accountants at Three Rivers Corp is 26 years with a standard deviation of 6 years. The average salary of the accountants is $31,000 with a standard deviation of 4,000. Compare the variation of the age and income. So I want to know which one is more variable, the age or the income. So what I want to do is I want to do a coefficient of variation for the age and one for the income. Okay? So for the age, I have that the mean is 26 and the standard deviation is 6. Remember that this is S divided by X bar times 100. So I have 6 divided by 26 times 100. So for my age, I come out to 23.1% for my age. For my income, I have a mean of 31,000 and a standard deviation of 4,000. I'm using the exact same formula. So I have 4,000 divided by 31,000 times 100. So 4,000 divided by 31,000 gives me 0.219 multiplied by 100 gives me 12.9%. Looking at these two, the larger percentage is more variable. Therefore, the age of the accountants is more variable than the income. Meaning you have a wider range for the ages overall, larger standard deviation based on what you have and everything for the ages than you do the income. May not seem like it because you're talking about thousands of dollars and you're just talking about a few years, but looking at the change in it, you actually have a larger variation based on when you divide that standard deviation out overall and everything. Okay? Practice some of these and you'll see. The last thing that we want to look at in this area is what we call the empirical rule. The empirical rule only applies to distributions that are normal and are bell-shaped. What I mean by bell-shaped is we have this distribution and it is very symmetric and bell-shaped, okay, with the center being here, can be cut in half and can be folded over on each other, extremely symmetric. This is what we call a normal bell-shaped curve. Okay? What this says is that in the center we have our mean. So the mean is here. The empirical rule suggests that if I go out and say the mean plus 1 standard deviation and the mean minus 1 standard deviation, so in between these two lines here, in between these two lines, approximately 68% of my data will fall. So 68% will fall in this red shaded area. Now if I move out further and go out 2 standard deviations, so I've got the mean, let me try this again. So I'm doing the mean plus 2 standard deviations and the mean minus 2 standard deviations, and I shade everything in between. So that's including the red, and I go out a little bit further. 95% of my data will fall. So this is 95%. So I include that original 68%, and then I've gone out further. Then, if I go out one more standard deviation here, I'm going to go out here, mean minus 3 standard deviations, and the mean plus 3 standard deviations, and color all of this in. So everything here, that's 99.7% of my data. So that leaves these little black tails, that is less than 0.03% of my data. Very little data falls here, according to the empirical rule. Most of my data, of course, 68% is here in this area. This is 68%. Okay. This 68%, that's a large portion of it. We take that and we add on another standard deviation. We're going to add on this green portion. So the red and the green accounts for 95% of the data. We go out a third standard deviation, and that's going to give me 99.7. A lot of times this empirical rule, you'll also see it written as the 68, 95, 99.7 rule. You'll want to practice some of these, knowing that, okay, if I go out 2 standard deviations, how much of my data is here? If I go out 3, how much of my data is between these? If I go out only 1, if I'm told that it's 95% of my data, how many standard deviations is that? Okay. Practice. If you need help, please let me know. Ask questions, okay?